Thanks a lot to the organizers for inviting me here. Especially it's an honor to give a talk on the 25th conference of Stereoscopic Displays and Applications. So, and you see here what I will present about. So it will be mainly about cell visualization, our topic. So let's dig into it. So first of all, a short introduction about this topic. So cell visualization, I think some of you always, when you are thinking back to the school time, you will think about the cell visualization which you see here. So one of the first visualizations was done by Robert Hooke. He did it in 1665. And since this time, people are thinking about how can they visualize cells. And this is also something we are doing. So since this 300 years, we have to think about how can we visualize cells. Of course, today there are a lot of different techniques, microscopy and spectroscopic techniques. And what we are thinking about is how can we visualize, how can we model cells. And this you can see here, this is our cell microcosmos project. I once started with this doing my bachelor thesis. So it's also coming now to the 10th year that I'm working on this topic. And I also did my PhD with that. So, and the main idea behind it is to combine bioinformatics with visualization tools. So we program our own Java 3D tools. We will see a few slides of this, a few screenshots, where we use also stereoscopic techniques. And in addition, we started 2 years ago to use tools like Blender, for example. I used in the past 3D Studio Max for the visualization, for visualization purposes. So, and the development went this way, that I worked with a lot of students always. So each semester I'm giving courses, projects or seminars where I present the different topics about cell visualization and also stereoscopic visualizations. And what you will see here now in the next, on the next presentation is a video which was done by 2 of my students, Chrstian and Tobias Hoppe. So it's, you will see it's not a perfect visualization, so especially at the demo session, you will see a lot more impressive work. I saw yesterday a few highlights of that already. And but what is important is they just started here. It was the first time that they did some visualization, so I gave them a short introduction to Blender. They had a course of stereoscopic visualization from me in those time. And so let's continue to first have a look at this movie. So please take your glasses on. It's around about 2 minutes. So to wake up. So the movie, what you see now, was shown the first time in 2012 in a cinema. So what you see is it's some blood vessels where some red and white blood cells are floating around. Now we are going down to the mesoscopic scale where we see different cell components, for example mitochondria, which are floating around here. So and in the background you see a Golgi apparat. Oh. In the background you see a Golgi apparat which is floating around. This is a nucleus which we are approaching now, and now you see how we are going through a pore. This is a nucleolus. And here we are now inside the nucleus, seeing the DNA, as you know. This is now the transcription process, where RNA is now transported outside of the cell nucleus. And now you see the translation, how a new, it's a way how a new protein is formed. Yeah. So much about the presentation. There will be also some other slides with stereoscopic effects afterwards. So now I'm coming to the problems which you saw here. So I think most of you are stereoscopic experts, so I don't have to tell you much about these problems, but I will mention them anyway. What you saw here is that the far plane and near plane are some on some places are not working correctly on some scenes. So, and if you see here in the center, there's a perspective plane, the position where the stereoscopic effect is optimal. So, and you see here also which tool we use. We use the stereoscopic camera plugin from Sebastian Schneider. You can download it online. It's compatible to Blender 2.6. And you see also this visualization was done by this stereoscopic camera plugin. So, and the problems which occurred, you see here it worked quite fine. This was a Golgi apparatus. It's also again stereoscopic. And you see here that we don't come across these borders. This means that we are inside this area between the perspective plane, which you see here on the top, and the near plane on the bottom. But then on the next slide, you see there was a mistake done. So you see when we float towards the cell nucleus, you see that here the particles on the front are, of course, the distance between these two particles is much too high. So, and you see that we are coming across this area, which you see here. I don't know, can I take this? Yeah, here. So the particles are inside this area here, and of course, this does not work fine in this case. So this is one problem we came across doing the visualization, but one specific problem for cell visualization is what we call the stereoscopic scaling problem. So, and we can solve this easily for cell animations, for example, but we see here what is the main problem about it. So we have to float from the mesoscopic scale to the molecular scale. So, and to come across this two different scales, we have a factor of 100,000 partly. So you see here, for example, when we are looking at light microscopy, we have some values around 1,000 or 10,000 of nanometers. But if we go down about confocal microscopy, electron microscopy, and spectroscopy, which you use to create here this protein visualizations, which you see on this side, for example, we are in an area where you are in the you have values of a few angstroms. So, and the problem is now if we navigate through a cell, we have to come across these very specific distances. So, and for rendered cell animations, it's of course simple. You saw that we just have different scenes, so you can optimize the effect. It was not done here, but we will do it in the future for future approaches. But in an interactive cell environment, it is indeed a problem, because when we freely navigate through our cell environment, which we are doing with our Java 3D tools, then you get really problems how to optimize the 3D effect. So, and here I show you a few screen captures, which I have done from our Cell Explorer. So you again have to take the glasses on, so that it works fine. So what you see here is an astrocyte cell in our Cell Explorer imported. So, and this is based on a real microscopic data set. So the visualization which you saw before, these were more abstract visualizations which were done with Blender. This visualization was done with tools like Amira, where you really look at each separate slide and you go through it like using Photoshop and to extract then the realistic shades of these cell components. So, and what you see in the center is now the nucleus, and if we navigate now to it, we come closer to it, and of course, when you use our tools, then it goes smoothly. This, for example, is the nucleolus now, and now we are inside the nucleus, navigating around, and at each step, the stereoscopic effect is optimized for this specific purpose. So what you see in the background are now the mitochondria. It's also interesting to mark the shape of this mitochondria because they are quite different what you know from school books here. Yeah, so this was the final screenshot. So, and what you see now, we implemented two different methods. So they are both not genius, but they are working quite well. So we have two applications. This one we integrated for our membrane editor. And this membrane editor you can use to create, based on PDB models, this is specific 3D models from proteins or lipids, which you can use to create cell membranes. Here you see such abstract cell membranes. So, and at each step, we just scale here the distance down. So we take into account the distance between the eyes and the center of our area, and by using this distance, we change the distance between the eyes and scale it down when we move closer towards the cell membrane, as you can see it here. The nice thing is that it works very nice for the center of our cell membrane, but if we have a very large membrane, then we have already problems to optimize the stereoscopic effect. So, and now when we are looking to our Cell Explorer, where I've shown you the screenshots before, then the problem is much more complicated because we have to come across very large scale differences. So here it's again about 100,000 in scale difference. So, and what we do here, we use a so-called pick ray in Java 3D. So we always adjust this pick ray here, this is on this position, to the nearest shape. So this means here this is a cell membrane, the abstract visualization of the cell membrane, and then we use a pick ray here to acquire the distance between the two eyes and adjust the distance between these two eyes, so the stereoscopic effect. So, and if we are moving now closer towards our cell components, we move across our border, so across the cell membrane, then he optimizes the effect to this nucleus here, for example, and if you are going more down, also to molecular structures, as you can see it here, for example. So, and then when we first submitted the paper for this conference, the manuscript, the reviewers told us, please make a better evaluation, because we showed it in the cinema, and everybody who we were talking to likes this movie very much, but of course this is not good enough. So we did some evaluation, and the most interesting question, which was also asked by the reviewers, was, you can see it here in the center of our table. So the question is it nice, but only a gimmick, or does it really make sense to work with these visualizations? So, and here we have three examples of our questions. So first of all, you see that how do you rate 3D stereoscopic approaches in general? Then how do you rate the 3D stereoscopic quality of rendered cell animations and what you saw before? So the students first had a look at our cell animation and had to fill out then a questionnaire. Then in the next steps, they were navigating through our cell environment with the same cell model which you saw before, and then we use the questionnaires of these 20 students to make an evaluation. So, and the average values, which you can see here, state that they are already very positive in terms of the stereoscopic effect. But then we see here, for example, question 2, this value could be better. But we think the problem, they were also reported, so we also had different questions in the questionnaire. So, and all of the students saw that there are problems with the stereoscopic effect, so they didn't like it so much. So, but here we see already, if we are looking to this interactive environment, we have left already the area of this value number 3, where they are saying it's nice, but just a gimmick. So they say it's good, and it makes sense to use it. But the most important question you see here, which was asked, do you think that cell visualization profits from 3D stereoscopic approaches? And you can see that here 18 of our students said, yes, it is this way. And I think all of you also know from evaluations, so we also had the 21st student, so he broke up after the first evaluation with the cell animation because he could not handle the stereoscopic effect. But I think this problems all of you know from your own evaluations. So some people just cannot stand this 3D stereoscopic effects. Yeah, what are the conclusions? So first, of course, for the rendered cell animations, when we do our future animations, we of course have to take into account this far near plane problem. It's well documented, of course. There are a lot of publications about that. We also cite some of them in our paper. Please have a look at it. Then, of course, there's a problem when we move between two different transitions. We have a transition between two scenes. We have to optimize the effect in terms where the eye focus is to acquire the stereoscopic effect. Then the interactive cell environment, I didn't mention it so far. Java 3D uses only the toe-in method. I think most of you know it. You can also have a look at the paper there. We describe it again. It should be substituted by an off-axis method. it's then for this we just have to change the perspective, the viewing metrics, and to make some new calculations. But it's not so easy to do this with Java 3D. If it would be a OpenGL native implementation, it would be no problem. Then in addition, we didn't give the users a chance to change the sliders, which changes the default value of the stereoscopic effect. And this is really something which makes sense to do this in the future, because everybody, as you know, has a different distance between, physical distance between the eyes, and for this purpose they have to adjust this distance. But it's, from our software, it's no problem, it works already. But our summary is cell animation is where profits from 3D stereoscopic visualizations in any case, but of course there are some important rules which have to be followed and have to be taken into account. So the outlook is we have to implement for our Cell Explorer and Membrane Editor the stereo techniques also for commercial techniques like NVIDIA 3D Vision. I implemented for the Cell Explorer, for example, a side-by-side view. This works already. I have to implement it also for the Membrane Editor. And currently, a new cell modeling project is running with around about 8 students. And one of the visualizations I want to show you here shortly, it's from Nicolas Pierre. This is a Clami cell, so a single cell floating through the ocean. So it's an interesting combination between plant cell and animal cell, as you can see it here. So here you see, for example, different chloroplasts. This was also done completely by using Blender. And these are only some first artworks out of that. So it's not finished by now, but he's working on that. So we come to the acknowledgements. So here are only listed a few papers which I was taking into account, but please see the publications. There are, of course, a lot of more authors which are working on this area. And then the acknowledgements go, of course, to my 2 students, which did a really good work. Then for the Cinemax Bielefeld, it's a large cinema in Bielefeld, which showed our 3D movie one time. And maybe also an additional time will come in the future. Then, of course, but what is very important, this open source tools, like to use Blender. So it's nice for the students to use them because they don't have to pay them, like 3D Studio Max, for example. They can also use them after they graduated, for example. And a lot of thanks go out to my participants from the Cell Microcosmos project. There's a URL where you can find it. And I thank you a lot for your attention. Thank you.